Hi, my name is Lindsay Bayak. I will be reviewing the DeFraudNet article, an end-to-end weak supervision framework to detect fraud in online food delivery. We all have placed orders online, and I'm sure you've had issues where your food wasn't exactly how you ordered it or how you expected it. Maybe it took forever to get to you, and maybe it didn't even arrive. The authors of this article are aware of that, and they know that there's legitimate concerns with food orders, but they're also aware that there are not very many solutions to detecting fraud. This would include ordering claims that there is reported issues when there really aren't. And this might be subject to a restaurant or food delivery service having to cover or refund those items, and these could be repeated claims. So the data also wouldn't be true. In the article in review, the authors described the machine learning framework that they created to detect abusive and fraudulent threats in this process of food delivery. Occurring online, these threats are things that are pretty difficult to detect in real time because of the difficulty in obtaining the strong labels for data. So the authors created an end-to-end pipeline for real-time fraud detection that works alongside a well-known algorithm, which then submits reported results through a class-specific encoder. The reports are evaluated and real-time decisions can be made for hundreds of thousands of claims to determine which have fraud-like features. So the authors also use a performance measurement of recall to ensure that the quality of their detection maintains precision levels and that it continues to show improvements in this ever-changing fraudulent environment. So we'll review their process, beginning with the 4 stages of DeFraudNet. So since DeFraudNet is the first end-to-end system of its kind that combines the label generation to serve a unified framework, there's 4 stages that we have to take into account. So number 1 is the data and feature pipeline, which is the important stage of building features that go into training, validation, and then creating what the authors call the golden data sets. The golden data sets have strong labels, and those are the ones that are best for detecting fraud. In the second stage, which is the label generation pipeline, these are where the weak labels for all the data points in the training and validation data sets are generated. Then we go on to the third stage, which is the discriminator pipeline. We're training the final discriminator models on features and labels from the last 2 stages occur. Then finally, the 4th stage is the evaluation stage, or the ablation study, which conducts the ongoing evaluation of the fraud detection system by sending a sample of claims to actual people and then using those recommendations to compute precision recall and any health check metrics. Here we have an overview of the stages in working order. So as you can see, the first stage of data and feature pipeline, the initial data set has all unclassified claims where a small random sample is sent to the risk management team. So initially they get it, and that adjusts cases to generate stronger labels that turn into the golden data set. So this golden data set is an accumulated data set over time, which is expensive, and it also takes time to generate because of its size. It takes a couple of months to actually collect that data. So there is more splitting in this initial stage of human labeled sets from the golden data set to use for the training data, and then to be used in the evaluation data set. So the majority of what is left over is then denoised, weak labeled training data sets. And in total, there's 4 types of data that is created from the first initial stage. This leaves us with having to set the features to be categorized. The 4 types of features that are categorized begin with F1, which is the historical features. These include the customer's name, the restaurant and delivery partner information. And then F2 is the real and near real-time features included in an open order or a current order, like a bill amount, the number of claims in the last 15 minutes, the time of day, and the type of claim. And then for F3, we have real-time transaction features. And these are those types of features that would be cross-sectional with current and previous orders to help capture the sequences found in the first two features. And finally, we have F4, which is the graph embeddings. And these are actually a subset of F1. So they mostly include the features relating to the restaurant and the delivery partner rather than the information about the customer. These are used in learning or determining who's responsible in the claim. And then moving on to the next stage, which is the label generation pipeline. This is where labeling functions are created manually with decision trees. So once the label functions are made, they're synthesized using the Snorkel generative model that creates label matrices. So 3 values are actually created from this, which is a 0, a 1, and a -1. -1 is considered abstain, and the abstain labels were less than 1%. So those labels were actually dropped from the training process. The labeling functions were also pruned at different accuracy levels, and they learned that the discriminator model in comparison to the new label data set, and then they tested the final performance on all of it. So in this stage, they found that 70% of the label functions had a 3.3% better F1 score compared to the whole model. The authors concluded that this was because of the ever-changing nature of fraud patterns and that the full set might not always be needed for the detection. They didn't give too much other detail about that either. So this comparison was done to check for errors in the reconstruction of the labels to make sure the training data is clean and won't manipulate the fraud type of data. So the box plots are used and they're set to a 75th percentile reconstruction of the 0 label type. So I mentioned that the data was categorized into a 0, a 1, and a -1. These here are showing the 0 label types. Moving on to stage 3, this would be the discriminator pipeline, where neural network-based methods are used to reduce categorical cross-entropy loss. Using this chart, it shows the combination of features and models together to predict fraud detection. So as you can see, the multi-layer perceptron is in this flow, includes the vanilla MLP, which includes the F1, the F2, and the F5 features that we had mentioned earlier. They're then transformed based on how they're originally distributed. So whether, for example, if they have a normal distribution, then they would be transformed into a z-score. And the authors found that making the network deeper like this didn't actually help the performance metric for recall that they ended up using. They also experimented with graph embeddings MLP on F4 using their formula, where each customer has a subset of F1. So here G is considered a homogeneous graph with single edge types. Any customer node that's embedded with a size of 128 are taken from the final layer of the GCN, which leaves us with an MLP graph embedding model that has 3 layers, which is explained later on in the performance metrics or performance evaluation. From their research, the authors tried out learning activity sequences are more effective in identifying fraud patterns. So they actually created the LSTM sequence model, which has 4 layers and 128 hidden units each, with 2 more thick layers that have 256 layers and 64 hidden units with ReLU activation using the Xavier initializer. As you can see from the graph, it gives you a better visual of how those are all working together. an overview of how this entire stage of deployment is shown in the training and serving infrastructure flowchart. This gives us a clear idea of how it all works well together online, as you can see from the top. And then underneath the dotted line is the offline version, where they use multiple platforms to create their working model. They work with TensorFlow, Spark, as well as a SQL type database to have it all work together. So we're back to reviewing the stages, just to have a reminder after this long journey of fraud detection, because at the deployment stage is when they do begin to detect the fraud. So we have to know how it all does in terms of performance and evaluation. The good customers, we want to make sure that, or the authors want to make sure that the study is avoiding identifying good customers as fraudulent. So that's why the evaluation process or stage is so important, because their ablation study design is based on quantifying the impact of various pipelines on recall where precision has been fixed at the same time or the same high value. Here we have the table of how DeFraudNet performed. And so the table shows that all the pipelines, which show that pipeline 2 uses only the labels from the layer functions and comes from a larger data set, has an improvement of 6.63% in comparison to number 1, which is nada. The auto layer function is pipeline 3, and it's the worst performer that the authors explain as the smallest data set, and it's limited by decision tree performance. The denoising pipeline number 4 shows improvement where they experimented with different modeling techniques to improve the discriminator by keeping the label generators in the same pipeline. They do this to measure for any value changes over time. In pipeline number 5, the MLP is replaced with the LSTM, which doesn't seem like their best improvement, but it only used one of the features out of all 4 of them. And so that's also the one that the authors had mentioned they are still researching the most and moving forward on how to improve it. Pipeline 6 is actually a result of pipeline 4, which shows the improvement recall of 11.42, and it has an added value from pipeline 4. So that one builds on the other one. And then finally, all components are totaled in pipeline 7, and that makes up the 16% improvement in recall. So the reasonable claims and the end results versus the missing information. From what I found to be reasonable in this article, it was that it was a creative solution to identifying fraudulent claims that would be difficult to identify, and as well where weak labels exist. Detailed consideration of features and their usage in the multiple pipelines was very clear to me. It was well organized. It used, it was a well-organized use of the data for more efficient pattern recognition. As well, it was interesting that the features that they had initially created in the first stage were used throughout the entire process for the detection process. As well, it seems to be user-friendly since it's commonly used algorithms and machine learning data frames. Some missing information that I had noticed was that there wasn't any additional explanation of why they chose recall for evaluation. And as I mentioned before, it would have been nice for them to compare the recall to the F1 precision, just to see how they do perform side by side. Overall, it seems like an expensive process to maintain, so it may not be for everybody. And it might only be for those companies who would be willing to take on the task of working with those different platforms, as well as maintaining the data sets over time. There wasn't any mention of how long it actually took to get the accurate results. And a concern might be that if it takes a long time for the data sets to build on each other, as it mentioned, months at a time, then it might be difficult for the learning processes to keep up with the changing fraudulent environments. There was a pretty big emphasis on the total recall rather when not all of the parts of the whole performed well. So they did mention that there were not all well-performing areas or stages. And so they really did emphasize that there was a 16% increase, which is the total of all of them. And there's a lot of different components in the infrastructure, which would be interesting to see how easy it is to detect any issues in accuracy. And finally, the next steps in conclusion. So the future work that the authors had mentioned was using variational encoders for naturally occurring data that is sparse but suspected as prone to be abusive. As well, there's more focus on improving the LSTM, which seems to be an important stage and component. And so that's good to hear that they are focusing on that, as well as further research of including the restaurants and delivery partners in the spread of fraud via different types of inputs. In conclusion, there was overall improvement, which is a plus in any case, and this can be applied to any industries that are similarly set up in ordering online. If you have any questions, please feel free to email me. Thank you so much for your time.